Hello again, everybody, and welcome back. In this video, we're going to be doing a couple of different things. We're going to be continuing our discussion on vectors and the different kinds of vectors. We've talked about the position vectors and displacement vectors. In the last segment, we got into velocity vectors and acceleration vectors. We're going to do an example right off the bat of a velocity vector, and then talk about acceleration vectors and how they're tied in, and then just do a quick little identification of different vectors based on what they look like and what they can do to other vectors. So, if that's not muddy enough, let's just go ahead and get started on this example 3.8. All right, so we have a fish moving, a rainbow trout. Of course, it could be anything, honestly. And we're given, this is actually pretty easy, we're given the vector of its motion, its velocity, because this is meters per second and meters per second. We're given this vector in unit vector notation, okay? So that means that it has an x component of 3.7, all right, meters per second. So I might say the x hat equals 3.7 meters per second, and it has a negative 1.3 y component. So we go down like this, negative 1.3 meters per second, and that's our y hat value right there. And of course, and that means that the vector is going to have the actual direction of motion is going to be like that. So that's going to be our velocity vector v. So all we want to do is find out the magnitude of that, all right, or with the magnitude being the speed, okay, just the magnitude of the speed, and also the direction of motion, that is that angle theta right there. Okay, so for the magnitude, for put something at the bottom right there. For magnitude of delta v, or sorry, of v, the vector v. Okay, well the magnitude, to find the magnitude, it's going to be the square root of the x value and the y value, right? So it's going to be the square root of 3.7 squared plus 1.3 squared. Of course, I left the minus sign out because when we square a negative, it becomes positive anyway. So what do we get for this? 3.7 squared, and I have to do it myself because I don't have it done right here. 3.7 squared plus 1.3 squared to the 1/2 power gives us 3.92. All right, 3.92. Well, in fact, I'm going to just truncate that to 3.9. That's what? That's meters per second, right? So that's going to be our magnitude. For our direction, theta is going to equal what? The inverse tangent of what over what? It's always the y over the x. All right, it's always the opposite. This is our angle right here. The y is the opposite side, and the x is the adjacent side. So it's going to be the y over the x. So it's going to be 1.3 over 3.7. And again, I made that just regular old 1.3 because all that we care about is the absolute value. We care about really finding what's called the reference angle, or that is the angle that is closest to the nearest axis. So just absolute values will do. So what is the inverse tangent of 1.3 over 3.7? For me, I get 19.4. 19.4 degrees. Now all we have left to do is just simply to state it all as one answer. So vector v is going to be equal to 3.9 meters per second at 19.4 degrees, and the last bit is what quadrant is that in? Well, we have positive x and negative y. That's going to be east and then south of east. So south of east is going to be our quadrant. South of east. I'm going to box that up, and that's our answer. All right, so that's just a little exercise on reassembling a vector from unit vector components, in this case being done with a velocity vector. All right. So that being said, we're going to move on to finding a change in velocity vector, and as such, we're going to find the acceleration as well. So here we have a car going around a corner. There's a famous scene in one of the older Batman movies from the late 80s where the Batmobile actually is getting away from bad guys, or maybe it's cops, I don't know. But to do that, to make a sharp turn, the Batmobile actually shoots out a cable, and it catches onto, I think, a street lamp or something like that, and it swings the car around, and then when the car gets to this point right here, it releases, and then the car can continue on its way. Meanwhile, the chasers, the pursuers, wind up spinning out. because they can't make the turn. All right, well, that's our Batmobile example right there. This is just going to be a regular old car, but it's the same idea. Now, there's no actual cable that comes out, but what is causing that, that inward tug is not just the cable, but it's just the tires themselves. Right? The tires being stuck to the road are going to be directing some sort of a force to the inside of that curve right there. And in doing so, they're going to enable the car to go around the corner. All right, so we're going to have something directed towards the center. So I'm going to mark that right there. All right. So this car is going at a constant speed. It's going at a constant speed of 12 meters per second. All right, so the car takes this path, kind of like that last little bit wasn't too great. Takes this path around the curve, kind of like that. But you'll notice that the velocity vector actually changes. I'm going to write this in green because it's written in green at the top. The initial velocity equals what? Well, it's got an x component, right? It's this direction at 12 meters per second. So 12 meters per second x hat. But there's no y component at all because this is moving entirely in the x direction. All right, so plus 0 meters per second y hat. All right, let's look at the final velocity now. Final velocity of this car is in a completely different direction. And remember, if you've got a change in velocity, whether it's a magnitude or direction, that means some acceleration is going to be involved. So we'll get to that in just a second. Final velocity, v final of the car, is going to be no meters per second in the x direction, right? Because it's moving entirely in the vertical, or in the y-axis right here. But it is moving. Remember, that plus sign is just sort of an and. It's like saying this x component and this y component right here. 12 meters per second in the y direction. But let's look more carefully at that. What do we need to do right here? Well, the y direction is directed downwards. It's in the negative y, right? So it has to say that it's a negative y component. All right, so negative 12 meters per second y hat. Okay, these are our two vectors that we have initially and finally right here. And so what takes place between an initial vector and a final vector, or an initial value and any kind of final value? Well, some sort of a change in velocity. Is what takes place between initial and final. And of course, we know that change means v final minus v initial. Change in anything always means final minus initial. So what we should be able to do to find this change in velocity from this direction at this velocity and at this speed and this direction at this speed is to subtract them, and we can do that using unit vector notation. In fact, this will actually be quite easy because we've got some zeros in here. Well, again, just to kind of remind ourselves what we're doing, why do we care about this change in velocity right here? It's asking about the acceleration, right? The average acceleration. Well, acceleration is average acceleration. Our definition for average acceleration is our change in velocity over change in time. We're given a change in time right here. We're given 10 seconds elapses. Question is, can we find our change in velocity? If we can, we should be able to easily find our change in or our acceleration. All right, so what direction is this acceleration on average directed in if this car is going to make this turn? All right, so let's find our change in velocity. All right, so velocity, delta v is going to be v final minus initial. So let's just, in fact, I'm going to move this up a little bit so because I'm going to run out of room otherwise. Final minus initial. So it's going to be the final x minus initial x, right? So 0 minus 12 x hat. I left the units off just for space, right? But it's final minus initial. And final minus initial y hat. So it's going to be negative 12 minus 0. Negative 12 minus 0 y hat. Well, that simplifies pretty easily. So it's going to be negative 12 meters per second x hat and negative 12 meters per second y hat right here. Okay, so what does that look like? What does that look like? Well, it's going to have a negative x component and a negative y component. All right, negative x and a negative y, like that. So our vector is going to be directed kind of like this right here, and that is what this shows us. So you've got an initial velocity plus, and look, this change in velocity vector is added, the tail of this change in velocity is added to the tip of the previous one. So they're being added together. So your initial plus some change results in your final velocity. Looks like we've done it right. Okay, so we have, we do have a final, we do have a change in velocity right here. Now I want to, what I'm going to do is actually go to a blank slide because I'm going to run out of space right here, and I don't want to do that. So we'll just start a new slide right here, and we'll go to it. So let's remember this. I'm going to rewrite it in just a second. Negative 12 meters per second x hat and negative 12 meters per second y hat. And we want to find that, okay? So let me quickly resketch our car. Yeah, I'll even try to make it look like the Batmobile a little bit with like fins on the back. All right, something like that. Big engine thing up front. And it's finally going this direction right here. All right, and there's the cabin thing and that. All right, so our initial velocity, V initial, 12 meters per second. All right, V final, 12, 1.5, that's not right, 12 meters per second. Meters per second, okay. So what has changed? Not the magnitude, but the direction has changed. And it's all a result of an acceleration. So this is swinging around like that and like that. All right, so we said that the velocity, this change in velocity from this to that was this. Delta V, change in velocity is negative 12 meters per second x hat and oops, negative 12 meters per second y hat. And I realize I just wrote right in the middle of it what I'm going to, sorry about that, I'm going to rewrite this because I'm going to want to be drawing here in just a second. All right, now remember this right here in the center is where the center of the turn was right here, so I got to leave that free. Our velocity, once again, our change of velocity, right down to the bottom here, delta V equals negative 12 meters per second x hat, all right, or in the x direction, and negative 12 meters per second y hat, or in the y direction. Okay, so what is the direction of the change in the velocity? Well, change in velocity is directed like that right there. That is our delta V because there's no longer any x value, and there is a negative y value, so this plus that results in this vector down here. Now, it doesn't look like it because this vector is at this location, but if we were to translate this up, because after all, vectors can be moved around, you just can't change their magnitude or direction, you can see how this plus that will give you that. All right? And I'm going to delete that right there. Okay, so what's the acceleration? The acceleration, we said, is going to be, in fact, let me see if I can move this. And I can't. I'm trying to move stuff around, but I can't. Acceleration, I'll just write it up top. Average acceleration is going to be our change in velocity over our time. All right, now velocity is a vector, and acceleration is a vector. Time is just a scalar right here, so time has no direction. So what this means is whatever the direction the change in velocity is going to be in, the acceleration is going to be in that exact same direction. Not the initial velocity, not the final velocity, but the change in velocity. So this change in velocity right here is going to be along the exact same line that the acceleration is going to be directed. Okay, so let's just find out what that is. Average acceleration. There's my arrow right there. So how do we find that? Well, we're going to write our change in velocity, so it's negative 12 meters per second x hat. I'm trying to write it small so I don't kind of clog up my space here. And negative 12 meters per second y hat. All right, that's the velocity. So we're going to divide each of those by time, by 10 seconds, by 10 seconds. So that means that the acceleration, the average acceleration, is going to be, what's negative 12 divided by 10? That's negative 1.2 meters per second squared now, right? Because it's meters per second per second. Meters per second squared, x hat, and negative 1.2 meters per second squared, y hat. That's going to be our x and y components of our acceleration. We're going to box that because that's going to be our final answer. So what that's saying is the acceleration is directed towards the center, the average acceleration. We say average because the acceleration actually changes as the car goes around the corner right here. We're going to see in just a second how at this point, in order for the car to start turning, the acceleration has to be directed towards the center. And then when it's at this point right here, it's going to be directed towards the center, and then towards the center, towards the center, towards the center, basically at right angles to the direction of the car and towards the center right here. But on average, if we took all those accelerations and added them up, it would result in one big average acceleration going right down this line, right in line, excuse me, with the change in velocity. All right? So this is our average acceleration vector written in magnitude and direction notation. In univector notation. If we wanted to find magnitude and direction, which we're not going to, but if we wanted to find magnitude and direction, we would simply square both of these, add them together, take the square root, like in the Pythagorean theorem, and we'd use our inverse tangent to find the angle. We would find that if the two legs, x and y, are the same length, that angle is going to be 45 degrees. But the magnitude will be something different that we're not going to get into. Okay? But the key here is that you can take a vector, and I didn't put an arrow over my delta v, my change in velocity vector right here. And you can take a vector and you can multiply it or divide it by some sort of a scalar and then get another vector. So this acceleration vector came from the fact that this is our change in velocity vector. All right? There we go. Last little bit right here, we'll take a few minutes to go through, and that's just identifying vectors. Kind of like we just talked about, the change in velocity vector is going to be along the exact same, well, the acceleration vector is always going to be along the exact same line as the change in velocity vector, because acceleration equals change in velocity over time. All right, so whatever direction this is in, this is going to be in the exact same direction right here. Okay? Now, it's not always going to be on that, it's not always going to be, let's just say this, the acceleration vector will always be in the same direction as the change in velocity, but it's not always going to be in the same direction as the velocity at any one point, the instantaneous velocity. And we'll talk about that in just a second right here. Depending on what the angle is between acceleration and velocity, you're going to have an object doing various different things. It might make more sense if we simply kind of just draw it out right here. Here, there we go. So we have this chart. All right, and so we have a velocity vector like that. Hopefully you can see that. It's not real bright. A velocity vector in that direction, and we have an acceleration vector in the same direction. There's our acceleration right there. What's going to happen? Well, the acceleration, now this is not change of velocity, this is just a regular initial velocity. And the acceleration is going to increase the velocity, and so that means it's going to increase. Kind of like what happens when you step on the gas pedal of your car, the accelerator. You go faster in that direction that you were going. All right? There's going to be no effect on the direction of motion because this is the initial direction right here, and the acceleration is applied in that exact same direction, so the direction of motion is going to be the same. Same direction, okay? But what if we have a velocity here, and we have an acceleration applied anti-parallel to it? What the anti-parallel means is in the opposite direction, 180 degrees opposite, okay? Well, what's going to happen to the speed right here? Well, you can be thankful for your brakes that they do this. The speed is going to decrease, all right? We say brakes are accelerators in that they are negative accelerators. They apply a negative acceleration to the direction that you're going. So that means you're going to slow down, but since these are once again applied all in exactly the same line along the same axis, there's going to be no change in direction. So same. All right? But now, what if we have a velocity vector here, and we have an acceleration applied at right angles to it? We just saw this. That's our acceleration right there. What's going to happen is, here's your initial velocity, here's your acceleration, so over as time elapses, your car is actually going to kind of curve that way because you have an acceleration applied at right angles to your direction of motion. All right. Now, will the speed increase or decrease? Well, they're at right angles, and so the acceleration is neither helping the velocity nor hurting the velocity because it's at right angles to it. It's not leaning into the velocity direction or leaning away from it. It's simply at right angles to it, and so there's going to be no change in speed right here. So, no change. But we are going to have a change in direction of motion. So, definitely changing the direction of motion as indicated by that the red arrow. All right, 2 more, and then we're just about done. Initial velocity, right there. What if acceleration is applied at an acute angle? That means a tighter than 90-degree angle. Well, we're going to have 2 things happening right here. First of all, it's going to help out your velocity, right? Because here's your velocity, and there is some little component of this acceleration, since it's at less than 90 degrees, that is pointing in the direction of motion. So yes, that will increase. The speed will increase. And the direction of motion will change as well. Change. Because you can see between those 2 vectors right there, your velocity is going to, or your car is going to take a path that is in between the velocity and the acceleration. All right, lastly, here's our velocity. Velocity, and we have an acceleration applied at an obtuse angle, that is greater than 90 degrees. There's our acceleration right there. What's going to happen? Well, first of all, we're going to have a change in speed, but look, this acceleration is acting kind of against the direction of motion right here. There's a negative component of this acceleration with regards to the initial velocity, and so the speed is going to decrease. Oops, I'm writing that in red. I'll keep it the same and write in blue. Decrease. But there will be a change in motion because you can see the direction of the initial velocity right here, and the acceleration is way back here, and so the motion is actually going to go like that. All right, so that's going to be our actual change in direction of motion. Very, very lastly, right here, we're almost done. What's going to happen at these 4 different spots right here? Here we have a velocity and an acceleration that is applied in a 180-degree opposite direction. The velocity is going to slow down. The direction is not going to change, but the velocity will decrease. All right, what about here? Here we have a velocity and an acceleration at right angles to it. What's going to happen there? Well, because it's at right angles to it, you're going to have a change in direction like that. And that's what's happening with that curve right there. Same with part B, or with number 3. As I say B, sorry, I meant 3, with number 3. All right, here we have our direction of motion. Here we have our acceleration, and so the result is that we're going to have a change in our direction of motion because accelerations create changes in velocity. And lastly, if we have an initial velocity in this direction and an acceleration applied to it, it's going to make the velocity increase because they're both in the same direction, but there's going to be no change in direction of motion. At least not until something else happens right here. Okay? So that's kind of a graphical understanding of the various different vectors. Don't forget that we also have vectors like position vectors. So between 1 and 2, I didn't really aim very well. But those are both position vectors that refer back to the origin. And this right here, between 1 and 2, we can call it a displacement vector. So that's like our final and our initial. There's initial and final positions. This right here would be a displacement vector that connects 2 positions right there. So we talked about position vectors, displacement vectors, velocity vectors, and acceleration vectors. Know how to identify them all and know what happens when they interact and affect each other. So that's going to be it for now. Thanks for bearing with me. This is kind of a long video, but we did cover a lot of things. And I hope that clears things up. So if it doesn't, please make sure you come see me. But in the meantime, thanks for watching, and I'll see you on the next one.